Welcome to implicit differentiation using partial derivatives. Remember, we performed implicit differentiation in Calculus 1. The formula below provides an alternative method for determining dy dx given an implicit function. Here's how it works. If an equation f of xy is equal to 0 defines y implicitly as a differentiable function of x, then we can determine dy dx by taking the opposite of the partial derivative of f with respect to x divided by the partial derivative of f with respect to y, as long as fy does not equal 0. So let's take a moment and see where this formula comes from. So we're going to start with f of xy equals 0. Now if our equation is not equal to 0, we can go ahead and move terms around so that it is equal to 0. And then what we're going to do is differentiate both sides of the equation with respect to x. And when we do this, we're going to have to apply the chain rule to the left side, meaning we're first going to find the partial with respect to x, then multiply that by dx dx, plus the partial derivative with respect to y times dy dx. Then of course the right side would be 0. Well, dx dx is going to be equal to 1. So now what we're going to do is solve this equation for dy dx. We'll first subtract fx on both sides of the equation. That's going to give us the partial with respect to y times dy dx equals the opposite of the partial of f with respect to x. And now we just divide both sides by fy, and we have our formula from the previous screen. Dy dx is equal to the opposite of the partial derivative of f with respect to x divided by the partial derivative of f with respect to y. Let's go and take a look at some examples, and we'll also compare this to the method we learned in Calc 1. We want to determine dy dx of this implicit equation. So it's already equal to 0, so we can go ahead and state that f of xy is equal to y to the fourth plus x squared y minus 12. So dy dx equals the opposite of, our numerator is going to be the partial of derivative with respect to x. So we'll treat y as a constant. That would be 0. This would be 2xy. This would be 0. And our denominator is going to be the partial derivative with respect to y. So we'd have 4y cubed. This would be plus x squared times 1, so plus x squared. This would be 0. So as you can see, it's a pretty quick, easy process. We have now found dy dx. Let's go ahead and compare this method to the method we learned in Calculus 1. So it's the same equation, but now we're going to use the method from Calculus 1. So we'll find the derivative of each term as we normally do, and if it has a y in it, we'll have to multiply it by an extra factor of dy dx because we'd be applying the chain rule. So we differentiate both sides with respect to x. So here we'd have 4y cubed times dy dx. Now here we're going to have to apply the product rule. So it would be plus the first x squared times the derivative of y, that would be 1 times dy dx, plus the second, or plus y times the derivative of x squared, that would be 2x. Derivative of 12 would be 0, and the right side would also be 0. And now we'd have to solve this equation for dy dx. So we're going to factor out dy dx, and then move this term to the right side. So we'd have 4y cubed plus x squared, and then we're going to go ahead and move 2xy to the other side, so we'll have negative 2xy. And now we divide. So as you can see, the first method was a lot easier and a lot faster. Let's go ahead and make sure the results are the same. Here's what we determined using the old technique. And going back to the previous screen, with a lot less work, dy dx of course is the same. Let's go and take a look at a couple more examples. Notice that this is not set equal to 0, so that means f of xy would be equal to sine x plus tangent xy minus 5. And now we can go ahead and apply the formula. So we have dy dx equals the opposite of this fraction, where the numerator is the partial derivative with respect to x. So we're going to have cosine x plus, so the derivative of tangent xy is going to be secant squared xy times u prime. Derivative of xy with respect to x is going to be y. Then of course derivative of 5 would be 0. We're going to divide this by the partial derivative of f with respect to y. So this derivative would be 0, and this is going to be secant squared xy times x. And of course derivative of 5 is 0 again. Let's go ahead and simplify this. First fraction would be negative cosine x all over x secant squared xy. Now for the next fraction, be careful of this negative sign here. The entire fraction is negative, so we'd have minus y secant squared xy all over x secant squared xy. So this part does simplify. So our final derivative would be negative cosine x over x secant squared xy. This would just be minus y over x. And let's go and take a look at one more. Let's go and write out f of xy. I'm going to write this as 2 natural log x squared plus y squared to the 1/2 power plus 3xy. This would be minus 4. One more thing we can do is we can take this exponent here and apply the power property of logarithms to simplify this function. Let's do that. So we'd have natural log of x squared plus y squared plus 3xy minus 4. Okay, let's see if we can determine dy dx. Don't forget the negative in the formula. So we're going to find the partial derivative of f with respect to x. Remember the derivative of natural log u is 1 over u times u prime. So we'll have 1 over x squared plus y squared. And then u prime, the derivative of x squared plus y squared with respect to x would be 2x, treating y as a constant. Plus the derivative of 3xy with respect to x would be just 3y. For the denominator, we'll find the partial derivative with respect to y. So we'll have 1 over u, or 1 over x squared plus y squared, times the derivative of x squared plus y squared with respect to y would be 2y, plus derivative of 3xy with respect to y would be 3x. So this is dy dx, but you can see it's kind of messy. So what we'll do now is clear the denominators by multiplying both the top and the bottom of this fraction by x squared plus y squared over 1. So let's see what this does. We multiply this fraction by this fraction. Notice the numerator and denominator simplify out, so we're just left with 2x. Plus, here we have to multiply 3y times x squared plus y squared. That's going to be 3x squared y plus 3y cubed. Let's look at the denominator now. Again, when I multiply this fraction by this fraction here, the numerator and denominator simplify out, so we're left with 2y. And then we have to multiply 3x by x squared plus y squared, so we'll have plus 3x cubed plus 3xy squared. Now it's very tempting to try to simplify the 2's and the 3's and maybe even some of the variables. But remember, we can't simplify across addition or subtraction, and since the numerator and denominator do not factor, this does not simplify, and we are done. In the next video, we'll take a look at expanding this formula here to help us determine partial derivatives, where instead of f of xy, we have f of xyz. I hope you found these examples helpful. Thank you for watching.